linked on. So, as I alluded to in this title, I'm going to be talking about star clusters in this talk, and this is a conference on galaxy formation and evolution, so you might be wondering, why should I care about star clusters? You should care about star clusters because, although they are the point sources of blue light in your galaxy images or your unresolved point sources in your galaxy simulations, these are the scales at which the formation of stars occur and the competition between stars, star formation and feedback, which dictate the outcome of the star formation process, play out. And these are also the regions where your H2 regions, which we use to infer a lot of our information on star formation, form and evolve. And so it's very useful to think of young star formation in galaxies as an ensemble of forming young star clusters interacting with interstellar medium. And this perspective has actually been quite useful in interpreting the properties of star formation in a local universe. So here's just an example of this playing out. So on the left here, I'm showing the typical cycle of gas in stars and galaxies. You have gas in the interstellar medium that collapses, condenses and collapses, moves in the cold dense phase. Then you have some star formation in that cold dense phase. And then you have feedback from young massive stars which act relatively quickly, which can destroy or evacuate some fraction of the gas, and some fraction of the gas ends up in stars. And this ejected gas can then participate in the star formation process elsewhere, and this cycle continues. And on the right here is another way of looking at the same thing, where you're seeing the cycling between the non-star forming and the star forming phase, driven by this physics of feedback and collapse. And once you reach the dense phase, one of the key numbers that's relevant here is what fraction of this dense gas ends up in stars and what fraction is ejected back into the interstellar medium. And for conditions typical of the local universe, observations and numerical simulations have converged in the idea that this fraction is relatively small, and a large fraction of this gas is ejected back into the interstellar medium on short time scales. And so you can see how this naturally provides an explanation for the long depletion times of star formation in galaxies, where essentially if you're a Lagrangian gas particle, you're just going around, very inefficiently moving about the galaxy, and the probability of you ending up as a star, even once you reach the dense phase, is relatively small. But as you heard, several times in this conference, the conditions at high redshifts, as JWST has revealed, are systematically different. And just one way of showing that in that they tend to be highly compact and forming stars vigorously. So here's a plot from Morishita et al. Showing the star formation rate surface density, which are 2 to 3 orders of magnitude higher than a representative sample of galaxies in the local universe for the same stellar mass range. And these compact starbursts, these are unresolved. These are galaxy observations. If you're lucky enough to have lensed observations of these systems, what you see is that they split up into compact star clusters separated by tens of parsecs, which dominate the rest frame UV light of these systems. And when you if you characterize the properties of these star clusters, as Angela Adamo did, you see that the stellar surface densities of these compact star clusters, superstar clusters as one would call it, is again 2 to 3 orders of magnitude higher than the representative sample of star clusters in the local universe. Now, what implications does this have on the physics of the system? In the context of this talk, I'd like to focus on 3 implications. One is that when you have more compact densities, your high densities are higher, and therefore your dynamical timescales are much shorter. And we heard this several times in this conference. Essentially, the clock runs much faster, and this has implications I will show in later slides. You can also show that the surface densities, which scale is proportional to the gravitational potential, well. And so this can impact the competition between star formation and feedback that plays out, as again I will show. And finally, a more subtle point is that in these more high-density systems, your escape velocities and your turbulent velocities are much higher. These tend to be more bumpy systems, and this can have distinct dynamical properties on the H2 regions that we would be forming. All right, so to explore these implications further, we ran some numerical experiments of star cluster forming complexes, and we trying to model or emulate the distinct range of conditions. And we do this by setting gas surface density of the systems ranging from 100 solar mass per parsec square to about 10 to the 5 solar mass per parsec square, which spans the range of typical cluster forming environments in spiral galaxies in the local universe out to these extreme systems that we're seeing. We are very careful with how we are modeling because the dynamical times of the systems are short, and so supernova occur too late to affect the the feedback star formation competition in the systems. So we've been very careful in how we're modeling the radiation feedback in the system, which we think is critical. Just to play the movie of what you're seeing, on the top left is the lower surface density, bottom right is the higher surface density, so there's 4 different surface densities. And this is a movie, so there's not much you can learn from it, apart from the fact that each panel evolves quite differently, as you can see, and I'll quantify what implications this have in the following slides. So the first thing, and we've heard this several times in this conference again, that stars form more efficiently at higher surface densities. And you can see this here. I'm showing the star formation efficiency as a function of time in these simulations, the different colors, the different surface density. As you go higher surface densities, you convert a larger fraction of stars, at which point the feedback is strong enough to see star formation in that system. And this is an experiment that's been repeated by several groups, several codes, different feedback implementations, and all of them, at least qualitatively, agree on this trend. And this comes down to simple physics on the competition between gravity and feedback, where you can show that the ratio of forces from gravity and feedback for a very simple spherically symmetric system scales with the surface density, and there's a critical surface density beyond which you cannot. The feedback doesn't have sufficient momentum to regulate star formation. And that critical surface density depends purely on the momentum available per unit stellar mass, which primarily depends on stellar evolution and the IMF, because most of the momentum comes from massive stars, and we don't have a lot of massive stars for typical IMFs. And so you get sort of this number for typical IMFs. So a natural question that emerges, we've heard a lot about, we discussed a lot about the possibility that the IMF may be different in the high redshift universe. So what impact might that have on this competition? So we again ran this experiment by playing with the IMF, but rather than trying to model the IMF, which is a horribly complicated problem, we assumed an IMF, and we assumed a more top-heavy IMF by changing the light-to-mass ratio, because there are different ways of getting a top-heavy IMF. You can have more massive stars, you can have a few very massive stars that dominate the luminosity. So we just played with this, and we spanned a large range of light-to-mass ratios, and we looked at the impact of the star formation efficiency. And as you can see, as you go to a more top-heavy IMF, you do indeed reduce the star formation efficiency. But as you go to lower metallicities, about 1% solar, you see that this effect is modest. And the reason is because the critical feedback mechanism regulating star formation in the systems is the radiation pressure on dust. And as you go to lower metallicities, you don't have dust, and so there's nothing for the momentum from the radiation to couple to in these systems. All right, so the next thing we looked at was in the context of Lyman continuum escape. So one of the things we saw was that, because these systems are more dense, the columns that these systems, that the denser systems have are much higher. Feedback has to really push through these columns to be able to evacuate channels for Lyman continuum escape. And so denser clouds need more dynamical times to carve pathways for Lyman continuum escape. So there's the time in dynamical times it takes to facilitate Lyman continuum escape. You can see it's much higher as you go to more denser systems. But again, this comes back to the point that this is in units of dynamical times, but the dynamical time itself is so much shorter for the denser clouds that the clock runs so much faster that in absolute times, when you see the escape, the Lyman continuum escape is facilitated at much earlier times. And this is simply because the clock runs much faster. And the cellular evolution doesn't care about the clock of a dynamical system. It's going to evolve in its, Lyman continuum photons are going to be, will stop emitting after a few million years. And so facilitating escape in that Goldilocks period is highly, highly important. And so, you see that the cumulative Lyman continuum photons emitted can be, a factor 100 higher. Some of this is from the higher star formation efficiency, you're forming more stars, but most of it is from the fact that you're facilitating escape when there are copious amounts of Lyman continuum photons are being emitted. So, what facilitates the Lyman continuum escape in these systems? Oh, sorry, just to provide an example of a system that that might be following this picture, you see in the sunburst Lyman continuum leaker a very dense star cluster that's leaking copious Lyman continuum photons, dominating the Lyman continuum leakage in this system. So what facilitates Lyman continuum leakage in our simulations is the radiation pressure-driven outflows in clumpy gas. You can see the gas distribution is highly clumpy. This is the sky map of the Lyman continuum escape fraction. You can see it's not at all uniform. It's in low surface density columns that are evacuated outward, and it's those channels through which Lyman continuum leakage occurs. And we also find that the the physics of radiation pressure-driven outflows imposes correlations between the velocities of the outflows in sight lines of Lyman continuum escape and the Lyman continuum escape fraction itself. And we overplotted some data points from local Lyman continuum survey galaxies where we have information on this, and it seems to fit this trend pretty well. Suggestive of possibly radiatively driven outflows facilitating Lyman continuum leakage in these local galaxies. Now, in this final slide, before I end, I'd like to touch upon some avenues that I'm exploring at the moment, and I'd really like for folks to talk to me about this. So one is, again, because of these distinct physical conditions in these galaxies, these star clusters, the H2 regions tend to have very distinct physical conditions. So what I'm showing here is comparing for, so this is for a typical local universe like H2 region from our simulations, and this is a more the more high density system. You can see the electron densities PDFs are much broader for the higher density systems, and I've superimposed some critical densities of some lines on this plot. And again, we heard some of this from talks by Yuichi and Lisa yesterday as well. H2 regions are not one zone systems. They have very complicated density and temperature structures. And all the more complicated when you go to these systems. Extremely high electron densities. We also find very broad distributions of electron temperatures, and we are in the process of exploring the implications of this by modeling the photo post-processing to get the photoionization states and modeling the nebular emission to see what impacts these distributions have there. Another avenue is, the devil is in the details, so we need to test these models and these ideas in systems that we think are similar to the systems that we're seeing at higher redshift. So we're looking at regions like, so there's a superstar cluster forming region in NGC 253, for instance, where you have very rich data on molecular gas and the PDR. But however, to compare to these systems, it's quite complicated because at these high densities, the chemical timescales are so short. It's much shorter than even dynamical timescales. The chemistry is very much out of equilibrium. And so to study the system, we've been coupling our simulations with non-equilibrium carbon and oxygen chemistry to try and see if we can learn something and test these models. Because all of these ideas are theoretical ideas, and just because we don't have a lot of systems that we can test these ideas on, and I think that's something that we need to all discuss and think about. So I'll leave you with that. The main point I'm trying to say is everything I've shown here today is not new physics. It's identical physics that we've used to understand star formation in the local universe, but operating in distinct conditions that we think we're seeing at higher redshift. But the point I'm trying to say here that the same identical physics in distinct conditions can lead possibly to distinct outcomes, and I think we need to talk more about this. Thank you.
Thanks for a very inspiring talk. I'm wondering, if you include Lyman alpha radiation pressure in your simulation, because I feel like some recent paper argue that Lyman alpha radiation pressure will dominate over, for example, Lyman continuum or far UV. Yeah, especially in low metallicity, high density environment.
100%. I think from a modeling perspective, from a feedback perspective, I think this is one of the biggest unknowns, Lyman alpha radiation. So no, the answer is no, we don't have it. And I don't think we're going to be able to do it for quite some time. The physics is just so complicated. And people have looked at idealized systems, spherically symmetric systems, and you can do this. But the minute you're doing this in dynamical simulation, I don't know. It just seems out of reach for now to me.
I see there's no mention of dust anywhere. Does that mean that's irrelevant? Or
sorry, can you repeat that?
Dust. Mm-hmm. Dust and metallicity relationships to those factors. Do they affect your analysis at all? You don't include. I don't see any mention of dust, and yet.
Oh no, dust is a critical agent. In fact.
Oh, good. I just see reference to it.
Yeah. So just to bring that up again, we see that when you don't have dust, you don't have anything for. Even if you have a lot of radiation from massive stars, there's nothing for the momentum from the radiation to come. That's right.
Yeah. So, sort of related. I don't want to trivialize the problem of high redshift star formation, but every now and then when we start talking about, oh, there's this incredibly dense thing, and special in all of these ways, I'm like, well, why isn't it kind of like the center of an ultraluminous infrared galaxy, which we already know a lot about?
It is, but I'm not sure we know a lot about it.
Yeah, but it doesn't. It's not exotic in the sense of something that has. I'm thinking about some of the language around, say, little red dots. It's like we've never seen this before. It's like, well, we've seen something kind of like it before.
No, 100%. I mean, my talk was, the final message from my talk is it's not exotic very much. But I think the issue is all of our inferences on star formation and our models have been inferred from local star formations, which are not at all like any of these star formations. I mean, you're right. We have systems like ULUGs. We don't have the level of detail that we can get from something like an Orion, which is where we learn star formation from.
We need to move on. Let's thank our speaker again. And I hand it